Hello CIO class, and welcome to another installment of Chemical Engineering Design. In this lecture, we will be going over non-Newtonian flow in the piping design handbook. Now in this lecture, we will cover very briefly the principle of rheology and differentiate between Newtonian and non-Newtonian flows, also understand what is meant by apparent viscosity, which is described in a textbook, and then also be introduced to rheograms, which you may have seen before, of various types of non-Newtonian fluids as they deviate from Newtonian fluids, and then also go over the exceptions and then some correlations which we will be able to use, which should be also used when we determine pressure drops for in the cases when we have non-Newtonian flows. Okay, so first off, what is rheology? Well, rheology is the study of how matter flows, and it's helpful to notice, at the microscopic level, what the fluid actually is. So at rest, shown here, we have the individual particles of matter, which we actually now know to be made up of wave fields instead of billet ball type particles. And these particles can be orientated or distributed with a certain orientation within a three-dimensional space. And that can be things like spaghetti-like, spherical, ellipsoidal, or chains of different spheres. And in the case where we apply a shear stress, so if we have a pump that applies a shear stress, or we've got a differential pressure head that induces shear stress on these particles will start to flow, and as such they will begin to interact with each other as well as reorientate themselves in space and interact with their surroundings. Now the following examples that are shown here are typical for polymers, oligomers, emulsions, elongated particles, and aggregates that will be found in things like clay slurries and wastewater treatment plants, etc. Rheology forms a part of or a branch of science that seeks to find ways at describing and understanding how non-Newtonian fluids interact under shear stress. And when we talk shear stress, we are actually interested in their viscosity, especially in designing pipelines. So this is applicable not only to liquids, it can also be applicable to polymer melts as well as solids, such as glass, which actually flows, as well as granite, which you may not have known, but also flows over time. Now, if we plot the shear stress against the shear stress that a fluid undergoes. So when we apply shear stress to a fluid, it will start to flow. And we can apply this shear stress at a certain shear rate. So if we plot the shear rate against the shear stress on these two axes, we obtain the following graph, and we refer to this graph as a rheogram, okay, for the study of the rheology of different fluids. And what we obtain are definite trends in these data that distinguish different and distinct types of fluids based on their respective rheologies. How do they interact with the shear that they are experiencing? With a higher shear rate, what is the shear stress that these fluids undergo? Now, the fluids that you are most familiar with are the Newtonian fluids, which comprise of things like water. Okay, so water is the most noteworthy example, and other examples are benzene, ethanol, carbon tetrachloride, hexane, and other fluids that are very simple molecules. So all of these molecules have one thing in common: they are very tiny. Carbon is very small, hydrogen is very small, and oxygen is very small. So whatever these three atoms are making up at a very small scale, low molecular weights, these types of fluids will generally be Newtonian fluids. Pseudoplastics, on the other hand, are characterized by a decrease in the shear stress as you increase the shear rate. Now, typical examples are polymer solutions. So sometimes you can formulate polymers within a solution. An example of this is when you make viscose rayon. You've got cellulose polymers which are dissolved in a specific type of solution, which is colored blue. It's a copper-based chemical. And another example is blood plasma, your greases that you'll find in your moving vehicle parts, molasses, as well as paper pulp slurries. Okay. Now, complementary to this are the dilatant fluids, which experience an increase in shear stress with an increase in shear rate. Now, the most notable examples are quicksand, cornstarch slurries, and potassium silicates in water. And finally, some of the fluids will act similar to pseudoplastics as before, except that these specifically require a certain amount of shear stress before they actually begin to flow. So you can imagine if you are hitting a bottle of tomato sauce to try and get the tomato sauce out, it doesn't want to flow initially, and then all of a sudden it comes out in one big splurt, okay, because it required a certain shear stress. And the same goes for clay slurries, toothpastes, mayonnaises, chocolates, and mustard. And remember, as chemical engineers, you might actually work with these sorts of fluids, and it's helpful to remember how these fluids react to your process as you're trying to move them through the process. Another type of curve that is often used is if you plot the viscosity against the shear rate, as shown here, and also in the textbook on page 59. The plot describes the behavior of dispersions, emulsions, polymer solutions, and slurries in general. The three regions that are present are namely a Newtonian region in the beginning, followed by a shear thinning region given by the Sicker model, and then a linear region that can be described by a power law model. Now, to describe the changes in viscosity, which of course becomes important if we wish to describe parameters such as the Reynolds number, we make use of the following general equation. Now, this equation equates the shear stress to the consistency term K, as well as the shear rate to the power of N. Now, just using this equation, first off, the exponential variable N is typically greater than 1 for shear thickening type fluids, and is also less than 1 for shear thinning fluids, and then equal to 1 for Newtonian fluids. It is also often done to separate this equation into two distinct terms, where the first term is the apparent viscosity given by n minus 1 multiplied by the multiplied by the right hand term, which is the Newtonian fluid based term, okay, where n is equal to 1. So for fluids that exhibit shear thinning, typically we would approach low shear rates, and as we decrease the shear rate, the viscosity increases more and more and will approach infinity. Whereas when we increase the shear rate, the viscosity will increase and approaches zero. Decrease, sorry, and then approach zero. So for shear thinning, at very low shear rates, viscosity increases to infinity. For shear thinning, the shear rate, as it increases, the viscosity will decrease and then approach zero. Now, in the case of shear thickening characteristics of fluids, the viscosity tends to approach zero as the shear rate approaches zero, while viscosity will approach infinity with the shear rate also approaching infinity. Okay, so two opposite responses, and I think the most important take home for this particular module is with this equation. If ever you need to describe the fluid properties, or you are designing a fluid flow process and you want to know what the viscosity is, and you would actually like a relationship then this equation is that equation which you would typically go to first as a general equation. And remember, because you have disturbances in a process, you have dynamics at play, etc. Flow can change, and you would like to know how do the fluid properties, such as viscosity, change with the change in flow, and also obviously the change in the shear rate. Okay, and with this, we end off the lecture for non-Newtonian flows, and the next lecture that we will cover will be multi-phase flow.